Hello, welcome to this lesson in Mastering Statistics. I'm Jason. I'll be your host and your teacher for this lesson and the next several lessons, where we're going to cover some of the most central and important topics in all of statistics. Because don't forget the whole purpose of statistics really is that we have a large population of individuals or something coming off of an assembly line or something that we wish to learn about, but because there's so many people in the country or in the world, we can never go survey everybody, right? So what we typically are trying to do is we're trying to do surveys and samples and trying to look at a small grouping of samples or of information that we can collect. And from that, we're trying to draw some conclusions. And sort of the whole topic of statistics is really trying to understand what conclusions can we draw. What can we learn about the population of the world by taking a small sample? And what are the limitations on taking that sample? And so up until now in statistics, we've learned a lot of the bedrock material. We've learned about the normal probability distribution and several other topics that have been really laying the foundation for what we're going to cover here when we're going to begin to start to talk about sampling, to start to learn about that larger population. So keep the big picture in mind. Right here we're going to talk about something called the sampling distribution, but it's dovetailing into other topics where basically we're going to be wanting to learn about the population that we're basically trying to study by doing some sampling. All right, so in this lesson, we're going to talk about sampling distributions. A lot of the stuff in statistics, believe it or not, seems difficult because the concepts seem fuzzy. If you read a textbook in statistics, a lot of times you shut the book and you're not really sure what you read because there's a lot of definitions. And if you don't take the time to really understand, really and truly what those definitions are, then when you get to a problem, you don't know what to do because you don't ever really take the time to understand the definitions. So I know it's a little bit long and drawn out, but we really need to take some time in this lesson and in the next lesson to understand some very important definitions and get our terminology down. The first thing is I want to remind you of something that we have already talked about. We've talked about the concept of a population, and I'm going to remind you of that here. The population is the large collection of things that we're really trying to study, but we need to study them indirectly because there's no way, for instance, if we're trying to study all of the adults in North America, that's millions of people. There's no way we can go and really study all of them individually. But we still consider that collection of people to be what we call the population. Now, when we take a sample, it is a small collection of people that we can then go and study. So I may take 35 people randomly from North America, and I may call that the sample. And I may go and calculate whatever it is. Let's say we're studying IQ. So we'll go give each of these people an IQ test, see how they score, and they're going to have some average IQ, but we would like to know how can we relate that information from the small sample that we have back to the population from which it came. Clearly, they're not going to be exactly equal. What are the odds that we happen to pick the perfect amount of people who scored in a representative manner the same as everybody in the country? We know they're not going to be equal, but we still want to know how we can draw conclusions from that small sample based on our what we're trying to study, which is our population. So when we talk about a sampling distribution, it's very similar to that concept that we're verbalizing here. We have a population, right? That's always going to be the same. And in this case, we just grabbed a sample of 50 people to try to study them. Now let me keep that in the back of your mind, and let's go turn your attention to something else that you have a lot of experience with already. Let's say you're making a cup of coffee. All right, so your cup of coffee is about this big, you've got some coffee in there, and you want to put some sugar in it. So what we do is we put the sugar inside, and we stir it up to dissolve the sugar, and then you take a sip, right? You're sampling the coffee. You're taking a sample. Now, clearly, the cup of coffee is very large compared to the tiny little sip that I'm taking. But when I taste it, I'm assuming that everything's well mixed in the coffee, and what I'm tasting is I'm making the assumption that what I'm tasting in my mouth is more or less the same as what is actually in the cup because everything's been mixed. But you know that unless you've really mixed it for a real long time, that's not exactly true. In other words, if I had a very large cup of coffee, let's say I work in a coffee factory where I'm making giant barrels of coffee like the size of a swimming pool. All right, so this is a giant swimming pool full of coffee, and I put sugar in one side of the swimming pool. All right, now clearly, if I take a sample from the center of the pool and test it for how sweet it is, either with my mouth or with some machine, right? I'm probably going to get a different answer than if I go right to where the sugar is being poured in. Let's say I'm dumping a giant barrel of sugar into the swimming pool. If I sample the coffee very near the sugar, it's probably going to be really sweet. If I sample the sugar in the center of the pool, or the giant barrel, it's probably going to be not quite as sweet. And if I sample the coffee at the far end of this barrel or this pool, of giant thing that I'm making of coffee, it's going to be probably less sweet still. If I mix it up for a long period of time, I assume everything will mix properly and then everything will be uniform. But certainly there are cases whenever I take a sample from here, and I take a sample from here, and I take a sample from here, and they're not going to all be the same. The same thing is happening when you make a sample, or you take samples of any kind of population. Let's go back to our example of IQ. Let's go and say, I want to study the IQ of everybody in the country. All right, so what I do is I go take 25 people from Texas, 25 people from Florida, 25 people from California. So I take 25 people, let's say I go make collections of 25 people, I put them all in different school buses, and then I give them an IQ test. Well, each set of people, each set of samples that I've collected from different regions of the country, of course they're going to score differently because all the schools are different everywhere, you know, and so on. So there's going to be regional variations because certainly different people from different backgrounds have different set of skills, right, is what I'm trying to say. So when you make a sample of something from a population, it's going to almost always be true that what you choose from sample A is going to give a slightly different answer from what you choose from sample B. If you don't want to think about IQs, you can think of things like maybe the height of people, how tall they are. If you want to look at all males in the United States, all right? All males in the United States. So if I go collect 25 people from California, 25 people, let's change the number. Let's say I collect 10 people from California, 10 people from New York, 10 people from Texas, 10 people from Connecticut, and I go get their average height. Of each set of 10 people, I'm calculating the average height of each set of 10 people I have, right? Each grouping of samples. Well, clearly I'm not going to get the same answer. I mean, there's going to always be differences, regional variations, you know, different ethnicities will yield different heights. And even if everybody is mixed uniformly, still not everyone grows to the same height. So the only thing I'm trying to get, I'm doing a lot of talking because I really need you to understand the concept of sampling something. If I go take a sample of 10 and another sample of 10 and another sample of 10 and another sample of 10 from any population of any kind, I can expect that I'm going to get average, if I take average values and average some quantity, whether it's height or IQ scores or anything, from different sets of people, I'm going to always expect to get different answers. But still, we like to do that because we can then collect the results and see what we can learn from them. All right, so let's talk about the concept of a sampling distribution, which is basically what I've just described to you without telling you what it is. When you have a population and then you go collecting a group of people or a group of information, calculate something like the average IQ or the average height, and I go do it again for another set of people, and again for another set of people, and again for another set of people, and I collect all that information, then what I've got is a sampling distribution because it's sampled, it's data taken from the population. That's why we call it sampled. But it's a distribution of values because sample A is going to be different than what I get from sample B, which will be different than what I get from sample C, which will be different than what I get from sample D. So they're a distribution. There's a wide variety of answers I'm going to get from my experiment, but I all know that they're going to be sort of related because I'm studying, you know, humankind or whatever. So I expect them to be tightly packed somewhat, but I expect them to be variations in the answers. That's called a sampling distribution. All right, so if I have different kind of distributions, just recall for a minute, distributions. There are several different kinds of distributions, you know, in the world, and we've studied some of them. And the most important one is called the normal distribution. We studied that significantly. A normal distribution is this thing that we call the bell curve, right? It starts out here, let me start here, kind of go down, never quite touches the x-axis, like that. So it's symmetrical about this line here. It never quite touches the x-axis on either side, but notice it has this nice bell shape. A lot of things in the universe really do behave like a normal distribution. A lot of things do. In manufacturing, in studying people, in studying heights, in studying lots of different things. If you look at the population large enough, many times you will get a normal type of distribution, where most of the population falls kind of near the center here, whatever we're measuring, and then as you get farther away from that average value, the chances of getting someone out there is less and less and less. It looks like a normal distribution a lot. This is called normal, but we have, of course, different kinds of distributions. Some we really haven't studied much. Here's one called skewed. This is a skewed distribution. And you can probably guess what that is. Basically, it's a distribution that's not symmetrical like this. So for instance, we could have something like this. Notice that these guys look sort of the same. They both have a peak here, but this one is very symmetrical, but this one is not. So a skewed distribution might be, just for instance, let's say I'm studying the IQ of people, but let's say my population isn't the world. Let's say my population is only the incoming freshmen of Stanford University or of MIT or some other top name university, right? Now I'm going out on a limb here, but I'm assuming that if people get accepted to Stanford or MIT or any of these other top schools, they probably have done pretty well in school. They probably have an above average type of IQ. So if you just look at the population of people coming into Stanford, their IQ is probably skewed to the right, and so you could have something that's non-symmetrical like that. You're not looking at a cross-section of the population of the world at that point, so you don't have a nice center value and everybody gently falling off. You're basically skewing things appropriately, because basically the selection criteria to those schools are throwing out some of the other people who are not in this range here. So that's a skewed distribution. I'm using IQ, but it could be anything. We could be studying the height of people. Certainly, if we're looking at the height of people in Asia, the height of people in, compared to North America, South America, different people based on their genetics have different average heights. So you could get a skewed distribution depending on who you're actually studying, right? And then there's this other thing that we don't really use too much, but I'll just mention it to you. I'll just write it over here. This is called a uniform distribution. A uniform distribution is basically when we don't really have a bell shape at all, but we have something like this. And there's not really a great practical example to show you that, but it's kind of a theoretical thing to show you that, in theory, you could have a distribution where every point here had the same probability or the same chances of happening. So if you whether you look over here or over here, you're basically going to have an equal chance of everybody falling in that area. If you're talking about heights or IQs or something, then it would basically be, no matter if you have a lower IQ or a higher IQ, you have exactly the same cross-section of the population at every little sliver there. So you don't have a nice peak showing an average value of things. Everybody is kind of equal, so to speak. And so that's a uniform distribution. The point is, these distributions, I want you to start thinking about them in terms of those are characteristics of the population. The population, whatever it is you're studying, whatever you've defined your population to be, has some distribution associated with it. Most likely it's going to be normal, but depending on what your population is, it could be skewed or it could be something else. But generally, we don't really know what the population is. If we knew what the population was, we wouldn't have to use statistics. We would just know everything. But really, if I'm trying to study all students in North America, I'm probably guessing that whatever I'm studying is most likely normal, but I don't really know because I can't sample everybody. So what I then do in order to study them, right, is I start taking surveys or samples. So what I do is I sample the population by selecting values. Now, when I say selecting values here, what I'm talking about is when you're sampling a population, usually you're talking about taking a survey of people. Like if I want to study the heights, the cross-section of heights in North America, I'll call them up on the phone and say, hey, what's your height? And they'll give me the data. That will be a data point, right? And I record that. But I may be working in a factory. I may not have anything to do with people. I may be studying candy bars coming off the assembly line, and I may be studying the length of the candy bar. Maybe every 1 million candy bars, the machine messes up and cuts candy bar in half. So I may go take a small cross-section. I can't study every candy bar. That would take forever. But maybe I go look at every 10 or every 20 candy bars or every 100 candy bars, and I use those as my random samples to see if I can learn anything about the population, which would be all of the candy bars that are being manufactured in there. So when we talk about sampling, what we're saying is we're taking a subset of the population and we're choosing to study them. All right, not a huge surprise there. So something you need to keep in mind is that the sample size is, in my lectures here, always going to be called N. In your course, they may label it a different variable. In almost every book I can think of, they're going to use N. So if you're working a problem or reading a chapter regarding sampling or sampling distributions, and it talks about the sample size of N, well then that's the number of people I'm choosing in this one batch to study. Remember how we said if we're going to study IQs, I might look at this 10 people over here, this 10 people over here, this 10 people over here, and I keep selecting cross-sections of 10 people. Well, the 10 people, the number 10 is my sample size, right? That's the size. It's how many people I'm choosing to study, and every time I do it. Now, I'm going to do it several times. That's not sample size. The sample size is how many data points am I collecting in one kind of unit to then analyze, and I may do that over and over and over again. All right, so the sample size is how many data points I'm going to collect at any given time. All right. Next thing to know is that, and this is important, so we're going to be getting into a little bit of math here. For each sample, which means for each little collection of people or things I'm studying, we can calculate a few things because I have some numbers now. I can calculate the mean of that sample. Whoops, not the mean, which is the average value. I can calculate its variance. I can calculate its standard deviation. Remember that? We studied standard deviation in previous lessons. I could even calculate some other values because statistics is full of different things you can calculate. But some of the most common things you'll ever find yourself studying when you're sampling is you're going to be calculating the mean, almost always calculating the mean, but you might be calculating the variance of the standard deviation. The mean is the average value. That's what the mean really is. So let's just say, for sake of argument, that I'm studying my population, the large collection of people is all students in North America. And let's say I'm interested in their IQ. So I'm trying to do a study and I want to see what is the, how is the IQ of all the students in North America, what can I learn about that? That's what I'm trying to do. Obviously I can't study them all, so I choose to set up a survey. So I choose some sample size, we call it N, and it could be whatever. We'll learn a lot more about sample size in a little bit, but let's just say I pick 50 people at a time because I'm employing people in a call center and I'm going to tell them, call 50 people, all right? So this person here calls this set of 50 people. I'm going to use my hands a lot in this class. So this set of 50 people is the sort of the first collection, the first sample. When I call it a sample, it's the collection of 50 people there, right? And from those 50 people, I can calculate the average IQ because this guy, this guy, this guy, this guy, this girl, this girl, this guy, they all have different IQs. But in my sample size of 50, I can certainly calculate the average IQ. So I can calculate the mean of sample number 1. Right? Then I go call 50 more people, and I can find 50 more IQs from sample number 2, right? And I can calculate the average IQ of sample number 2. And then I can do it again and again and again, and call another 50 people, and call another 50 people, call another 50 people, but every time I do it, I average their IQs, find their means, and then I'm basically recording the average IQ I'm getting from each batch of 50 people. These are important concepts, very important concepts that are going to come back when we study the central limit theorem in the next section. So that's why I'm taking some time here. But basically what I'm trying to say in the third bullet, you can calculate things. I can find the standard deviation of their IQs. That means how spread apart are their IQs about its average, about the average IQ from that sample. I can calculate things for each sample. All right. This is important because it's directly related to what we're talking about here. If I choose every possible sample of size N from my population, and I'm going to write population as population. Then I'm going to write something in red, or in pink here. then what I get a sampling distribution. I'm going to put it in quotes here because this is a term. You know, the important terms here I'm trying to pull out for you. Sampling distribution. You have to understand the terminology. I mean, if you're reading in the book, hey, the sampling distribution of the IQs of, you have to know what they're talking about. When you see the term sampling distribution, it means that someone spent a lot of money and time trying to collect this information. What they did is they said, all right, we're going to have a sample size. It's going to be a certain size, let's say 50 people or 20 people, and we're going to collect this sample and then this sample and then this sample, and we're going to collect as many as we can. But if we somehow could collect them all from our population, we can organize it into something we call a sampling distribution. So in the case of IQs, let's say, I have an IQ here, an IQ here, from this set of 50 people, from this set of 50 people. If I find the average IQ for every sample from every set of 50 people, I'm going to get a bunch of average IQs from everybody, and I can, of course, plot them in a histogram, and I can find out that most of the time, what I'm getting is an IQ that's representative of my population. We're going to get to that a little bit more later, but the point is, this is called a sampling distribution. If I take that information and I organize it, if I organize it into a curve of some type, that's called a sampling distribution. And then the final thing I want to say here is what I've basically just said. If we calculate the mean of every sample, all right, then what we get is a very complicated sounding thing, but it's not very complicated. What we get is the following. We get a sampling distribution of sample means. Don't overlook how important these words are here. It's very descriptive. It's a sampling distribution because I got the information by sampling the population, by going and collecting information. That's what the first part means. Of sample means, right? So as I said before, let's say it was IQ. Let's get away from IQ. We want to talk about the same thing over and over again. Let's talk about, you know, oh gosh, it could be anything. Let's say we're going to sample everybody in the country and we're going to ask them, how many siblings do you have, brothers and sisters, right? So clearly they're going to give you a number back, right? So let's say my sample size is now 20. Sample size N, that's 20, right? So I go ask the first 20 people, how many brothers and sisters do you have total? Well, this guy, this guy, this guy, they're all going to give me different answers, right? But I can take that information from that sample and I can calculate an average number of brothers and sisters. Maybe it's 2.5 or 3.2 or whatever it is. I can calculate that number. That is a sample mean because this is a sample, a stack of 20 people that I've called, and I'm calculating the mean. Okay, then I go do it again. For this stack of people, I go randomly choose those from the population. I get another sample mean, which will be different than the original one because the odds of them being the same are very low, right? They have exactly the same amount of brothers and sisters. But I can do this process again and again and again, asking everybody, every stack of 20, how many brothers and sisters do you have? They will answer, and then I can calculate a sample mean. Now, if I do this for the whole population, which is really impractical, I mean, you're really not going to be able to call everybody in North America, but what you get whenever you theoretically call everybody in terms of the sample mean, get the sample means like that, then what you get is a sampling distribution of sample means. That's what you get. And that's what I'm really trying to teach you in this lesson is the terminology. The sampling distribution is when you get that information and you're getting a distribution of answers, and usually when you do that, you're calculating something. Usually it's the mean or the standard deviation or whatever it is you're trying to study, but that's called a sampling distribution of sample means. There are other types of sampling distributions we'll get into later, but mostly we're going to talk about sampling distribution of sample means. So what I'd like to do is close the section down here. Mostly wanted to give you an introduction what a sampling distribution is, the concept of a sample size, the concept of a sample mean, and then the idea that if you do that enough, you get a sampling distribution of sampling means. Now in the next section, we're going to study something called the central limit theorem, which is directly going to come from where we ended here, and we're going to be able to tie some numbers to it and see what we can actually learn. So far, we've just been doing definitions. I haven't really told you what a sampling distribution of sampling means is really useful for. In the next section, with the central limit theorem, you're going to learn why it's useful. So don't feel too bad. We haven't done any problems here. We're just getting our feet wet. We're just learning. Follow me on to the next section with the central limit theorem, and you'll see how to use this stuff and how to solve real problems.